random variables and its probability. Consider the experiment of tossing a coin 2 times in succession. Now, when a coin is tossed, there are two possibilities. So, the sample space S equals possible outcomes on 2-time tossing, which is equal to HH, HT, TH, and TT. To come randomly head or tail is known as random variable. Random variable is denoted by X. If X denotes the number of heads obtained, then X is a random variable, and for each outcome its value is given as XHH equals 2, XHT equals 1, XTH equals 1, and X of TT equals 0. More than one random variables can be defined on the sample space. Let y equals number of heads minus number of tails. Then YHH equals 2 minus 0, that is 2. YHT equals 1 minus 1, that is 0. YTT equals 0 minus 2, that is minus 2. Definition: a random variable is a real valued function whose domain is the sample space of a random experiment. Let's take an example. A person plays a game of tossing a coin thrice. For each head, he is given rupees 2 by the organizer of the game, and for each tail, he has to give rupees 1.5 to the organizer. Let X denote the amount gained or lost by the person. Show that X is a random variable and exhibit it as a function on the sample space of the experiment. Solution: you can see all the possibilities shown. So, the sample space S is as shown. Then, X of HHH equals rupees 2 into 3, which is rupees 6. X of HTT equals X of HTH is equal to X of THH, which is rupees 2 into 2 minus 1.5 into 1, that is rupees 2.50. X of HTT equals X of TTH equals X of THT is equal to rupees 2 into 1 minus 1.5 into 2, that is equal to minus rupee 1. And X of TTT equals minus rupees 3 into 1.5, which is equal to minus 4.50. Therefore, the range of X, that is the outcomes, equals 6, 2.5, minus 1, minus 4.5. Example: A bag contains 2 white and 1 red ball. One ball is drawn at random and then put back in the box after noting its color. The process is repeated again. If X denotes the number of red balls recorded in 2 draws, describe X. Solution: let the balls in the bag be denoted by W1, W2 and R. So the sample space is as shown. X of omega is equal to number of red balls. X of omega 1 equals X of omega 2 is equal to X of omega 1 omega 2 is equal to X of omega 2 omega 1. All are equal to 0. Similarly, you can see the other cases as well. Thus, X is a random variable which can take values 0, 1 or 2. Probability distribution of a random variable. Let us consider 5 families and its members F1, F2 up to F5 and having members 3, 4, 3, 2 and 5 respectively, as you can see. Thus, X can take any value 2, 3, 4 or 5 depending upon which family is selected. Now, X equals to 2 for F4, X equals to 4 for F2, X equals to 3 for F1 or F3 and X equals to 5 for F5. So the probability for number of families selected for X equals to 2 is P of F4 equals 1 by 5. For X equals to 3, P of F1 F3 equals 2 by 5. For X equals to 4, P of F2 equals 1 by 5. And for X equals to 5, P of F5 equals 1 by 5. These expressions of probability are called probability distribution of the random variables X of the system of numbers as shown. Also, P1 plus P2 up to Pn equals 1. That is, summation from I equals to n, Pi equals 1, where I equals 1, 2, 3 up to n. Example: 2 cards are drawn successively with replacement from a well-shuffled deck of 52 cards. Find the probability distribution of the number of aces. Solution: the number of aces is a random variable. Let it be denoted by x. Clearly, x can take the values 0, 1 or 2. Now since the draws are done with replacement, therefore the two draws form independent experiments. Therefore, probability of x equal to 0, that is probability that none ace and none ace, that is equal to probability of none ace into probability of none ace, is equal to 48 by 52 multiplied 2 times, that is equal to 144 divided by 169. Probability of x equal to 1 comes out to be 24 by 169, and probability of x equals to 2 comes out to be 1 by 69. Thus, the required probability distribution is as shown. Example: find the probability distribution of number of doublets in 3 throws of a pair of dice. Solution: let x denote the number of doublets. Possible doublets are 1 1, 2 2, 3 3, 4 4, 5 5 and 6 6. Clearly, x can take the values 0, 1, 2 or 3. Now probability of getting a doublet is 6 by 36, that is equal to 1 by 6. And probability of not getting a doublet is 1 minus 6 by 36, that is 5 by 6. Now probability of x equal to 0, that is probability of no doublet, is 5 by 6 to the power 3, that is 125 divided by 216. Probability of x equal to 1 comes out to be 75 by 216. Similarly, probability of x equal to 2 comes out to be 15 by 216, and probability of x equal to 3 comes out to be 1 by 216. Therefore, the required probability distribution is as shown. Example: let x denote the number of hours you study during a randomly selected school day. The probability that x can take the values x has the following form, where k is some unknown constant. Then probability of capital X equals small x is equal to 0.1 if x equals to 0, k into x if x equals to 1 or 2, k into 5 minus x if x equals to 3 or 4, and is 0 otherwise. Question A: find the value of k. Question B: what is the probability that you study at least 2 hours, exactly 2 hours, and at most 2 hours? Solution: the probability distribution of x is as shown. A: we know that summation pi I equals to 1 to n is equal to 1. Therefore, 0.1 plus k plus 2k plus 2k plus k equals 1. Therefore, k is 0.15. B: probability that you study at least 2 hours is probability of x greater than equal to 2. That is probability of x equals to 2 plus probability of x equal to 3 plus probability of x equal to 4, which comes out to be 0.75. Probability that you study exactly 2 hours is probability of x equal to 2, that is 0.3. Similarly, probability that you study at most 2 hours is probability of x less than equal to 2, which is equal to 0.55.